Now we will continue to speak about planets, but only on one planet, that is the Earth. And we will try to look at what happened during the first 500 million years of our planet. So I suppose that many people spoke about this, the formation of the solar system with the collapse of an interstellar cloud, formation of planetary disk, formation of planetesimals, formation of the giant planets, and at the end, formation of the telluric or Earth-like planets. So, as I told you, we will focus on the history of the telluric planets. And if we look at the history of the Earth, it can be subdivided into four periods: Hadean, Archean, Proterozoic, and Phanerozoic. So each limit has a meaning. Of course, the beginning is the accretion of the Earth, and we will see what we can think about this event. The second limit is 4 billion years. This is the age of the oldest rock known today. So maybe you have seen yesterday evening the Akastagnisis. These are the oldest rock. And the mark today is the limit between Archean and Hadean. The other limit is 2.5, is the limit between Archean and Proterozoic. And this is what we could call the beginning of modern Earth. This is the moment when some kind of modern-like plate tectonics appears on Earth. Plate tectonics was working before, but the detailed modality of this plate tectonic were different from plate tectonics today. So modern-like plate tectonics appear at that moment. At 0.5, at the end of Proterozoic, this is the explosion of life, or not of life, but of fossils at the limit, at the beginning of Cambrian, here. And of course, the last point is today. So I put a value here for the beginning of the history, for the beginning of Archean. It's 4.568 billion years, and I would like to discuss the meaning of this. So what is, for the Earth history, what is the starting point? And it's quite difficult to decide when we will start the story. Of course, some person, probably you know this person, try to determine when the history of the Earth began, and so at that time that was when the God created the Earth. And of course, his study was based on the age of patriarchs in the Bible. And of course, the result is something extremely precise. So the Earth has been created Sunday, 23rd of March, 4004 at 9 a.m. So this is amazing result and unbelievable. This is the reason why we do not believe this age. And we'll try to find another way to discuss this. And one answer may be provided by a meteorite, by a chondrite. So here is a carbonaceous chondrite. So it is made of chondrules, and these chondrules contain minerals, just like, for instance, here, olivine, but also glass, iron, or other minerals, just like pyroxene. Okay. These meteorites are very interesting because they are considered very primitive, because they have almost the composition of the solar photosphere, if we accept, of course, volatile elements. But here we have the composition of the solar photosphere. Here we have the composition of this chondrite, and all the elements, each point represents one chemical element, fall on a line here whose slope is 1. So that means that the composition on this line is the same for the chondrite and solar photosphere. So except some elements, as Francis said a few minutes ago, well, this is a criterion to say that these chondrites are very primitive. Just to continue with this aspect, here we have primitive carbonaceous chondrite, so with all elements, I excluded the volatile element, falling on this line, whose slope is 1. And if we compare this with what we call a differentiated, here this is an achondrite differentiated body, we can see that in this case, if the body is differentiated, so that means that it is not primitive, the points do not fall, or only 1 or 2 fall on this line, and there is a large scattering of data. So this is used as a criterion to distinguish the most primitive object in the solar system. And this, of course, these chondrites here are considered as very primitive objects in the solar system. So we have the chondrule here, but something very interesting is what we can find in this meteorite, other objects than the chondrules, which are these inclusions. So this white inclusion here, and of course, if we look at the relationship between the inclusion and the rest of the meteorite, it seems that these inclusions are older. Just like when you look at the granite, sometimes in the granite there are inclusions. These are inclusions of rocks that were there before the emplacement of the granite. So here, the relative chronology is that very probably these inclusions are older than the chondrule here. So inside this meteorite, we can find two kinds of objects from the point of view of chronology, old ones and younger ones. So here is the same if we look at Allende meteorite. And if you want to see Allende meteorite, you have to look at the neck of Muriel. She has a piece of Allende meteorite around her neck. So here is with a cathodoluminescence picture of one of this meteorite. And each color represents one element. In red, we have the magnesium. So we can see that most of this chondrite with a chondrule here contains magnesium. And of course, we have seen that this is mainly olivine, and olivine is a silicate of magnesium. So there is a lot of magnesium in olivine. So this is quite logical to find everywhere here magnesium. But the inclusions here contains aluminum and calcium. So the composition of the inclusions is different. That means that we have seen that the inclusions are older, but they are not only older, they are also with a different composition. And of course, as they are rich in calcium and in aluminum, so blue and green here, they are called calcium aluminum rich inclusions. So it appears that these objects that are older than the meteorite itself are not, as I said, only older, but also with a different composition. So one picture that is is more or less the same as one of the tables presented by Francis. Here is the temperature of condensation of different kind of material. And what we have, for instance, water at atmospheric pressure is 0 degrees and so on. And we can see that at very high temperature, we have this kind of inclusion, refractory inclusion. So CAI is for calcium aluminum rich inclusion. After we have metal, silicate, and so on. So what says this kind of table is that this calcium aluminum rich inclusions have a very high condensation temperature. So in the protosolar nebulae, they should correspond to the first object that can condensate or that can crystallize. So this is in agreement with the relationship we can see in the meteorite. These objects are older, and theoretically they should be older due to their composition. So this is quite logical. Okay? So certainly the age of this inclusion is older, greater than the age of the chondrule. And some of these objects were dated using uranium-lead system. So here is a product of disintegration of uranium, it's lead composition. So the CAI inclusions give ages that are very easy to remember, 4, 5, 6, 7 million years. So more or less the same for this, the two samples, while the control give younger ages that are 4, 5, 6, 4 million years. So, okay, here it seems that there is more or less between 2 or 3 billion years between the condensation of CAI and the condensation of the rest of silicates that form the control. Another approach is based on extinct radioactivities, just like, for instance, 26 aluminum that decays in 26 magnesium. So the half-life is very short, less than 1 million years. And of course, all 26 aluminum disappeared in less than 7 million years. So if, as the inclusion contain an excess of 26 magnesium, that means that they condense less than 7 million years after the nucleosynthesis formation of aluminium-26. And as there is no excess of magnesium in control, that means that they crystallize after. And from this kind of diagram, where we have isotopic composition of magnesium and here of aluminium, we can distinguish a line here for the CAI inclusion, and this line for control. And of course, here this kind of approach also indicates that 2 to 3 million years elapse between the condensation of CAI and control. And finally, where is it? So here are different ages obtained on this object with different methods. And finally, the value that people consider as being the value of formation of the T0 for the solar system is this age of 4,568 million years. So this age is something established with a good accuracy. You can see that the error of age determination is very low. But there is some kind of problem with it, because we try to date the formation of the solar system. And the formation was not made, the solar system doesn't form in 1 second, but elapse over a time range. And for instance, this age, that is the condensation of the inclusion, is of course younger than the age of the real beginning, when the protostellar clouds began to collapse. So, okay, this is not the real beginning. We also use this age as the age of the Earth formation. But of course, these inclusions here form before the formation of planetesimal and before the accretion of planetesimal that result in Earth formation. So this age is slightly older than the real age of Earth formation. I speak about Earth as a planet. So, okay, we have an age with a very small error on age determination, but everybody uses this age, but this is not perfectly the age of the beginning of the solar system or the age of the beginning of the planet Earth. So we will use this age, but you must know this limit and this restriction on the validity of the age. Okay. So this is the first point. This is the beginning of ADN. So the end of ADN is the age of the oldest rocks. So first, these oldest rocks are coming from Acasta here in the Northwest Territories in Canada. And this is a very small outcrop. Acasta gneisses are on this small island here and a small part here. So the access is not very easy. The best way is to use this kind of thing. And as this is a very important place, Canadian geologists built a small house to welcome geologists from everywhere in the world. And you must notice a very big barbecue here, which is very important. So the rocks are like this. You have seen samples yesterday evening. So these are gneisses, gray gneisses here. And for instance here, they are cut by a young rock at 3.6 billion years. So here is one of these Acasta gneiss, and it contains zircon crystals. So you have one here, and you have each cycle here is a spot of analysis of this zircon grain, and you can see that the age is slightly older than 4 billion years here, and so on. So it's around 4 billion years. And these rocks are the oldest known today. Something interesting is this sample on the border of the lake. And you can see that one part of the sample is broken. So you have here a picture of a nice broken rock. And of course, what is the interest of this is that this sample contains zircon crystals at not exactly 4 billion years, but at 3.9 million years. And you can see that this age is the age for the border, for the rim of the crystal. But inside, there is a core. I think that the color of the core, you can see, is not exactly the same. It's a gray, dark gray. And the ages obtained on this part are 4.2. So 200 million years older than the external part of the zircon crystal. So that means that, in fact, this rock has a very complicated history. For instance, the age of crystallization of the rock, of the samples you have seen, is this age, 4 billion years or 3.9 million years. But there are remnants of older rocks. And what you must keep in mind is that zircon crystals are very resistant to weathering and all kind of alteration. So very probably there was, before this Acasta gneiss, there was a granite. This granite was weathered, transformed into sediments, and as zircon is very resistant, it remained as a detrital part in the sediment. And when the sediment underwent melting, of course, this very old zircon were used as a nucleus for the crystallization of younger zircon. But what is important is what shows this sample is that, of course, the rock has an age of 4 billion, but they contain an older core. That means that before these rocks, even if we do not know rocks at 4.2 billion years, it existed in this part of the world, rocks of granite at 4.2 billion years. So there were Hadean granite and Hadean continental crust in this part. We do not know this crust. It disappeared, but this is a proof that this rock existed. Okay. Maybe you have seen, this is a paper published in Science many years ago, 8 years ago, in 2008. And the people who published it, O'Neill, proposed that they found some rocks in Canada. And they proposed that the age of these rocks would be 4.3 or almost 4.3 billion years. So they would say, okay, these rocks correspond to Hadean mafic crust. And of course, if this is true, these rocks are older than the Acasta gneisses. So they come from Nuvagituq, which is a place in Quebec here, north of Hudson Bay. So in Canada again. And, okay, the place is very strongly eroded by ice cap. So we can see very well-polished rocks, and you can find sedimentary rocks. Here we have this kind of sedimentary rocks. You can see the layering of the sediments. And some bounded ion formation, as here. And one rock, which is very special, it's some kind of amphibolite. So here is a better view of it with a garnet. The red points are garnet. And I think I have a better view. So maybe you know what is an amphibolite. An amphibolite is a rock that contains amphibole. And generally, amphibole is black. And most of the amphibole you can see at the surface of the world are black. Here, this is a very special case. The amphibole is a cummingtonite that is a white amphibole. This is the reason why the people at the beginning, the geologists who work there, call this faux amphibolite, that means false amphibolite because it is an amphibolite, but it doesn't look like amphibolite. Some kind of Canada Dry or something like that. So, okay, the composition is amphibole, biotite in black, and garnet in red. So this person performed dating using extinct radioactivity, the decay of samarium-146 into neodymium-142, and they obtained this age here of 4.28. But you see that, okay, they can draw a line, but there are some points outside of the line. And they force the line to go through the modern terrestrial value. Okay, but there is a line at 4.3. One of the problems is that when you take exactly the same sample, but that you use another system, which is the decay of 147 samarium into 143 neodymium, the age is 3.8. So we have, on the same samples, two isotopes of the same element that give absolutely different ages. So this is one part of the problem. And recently, there was a lot of papers that say that because people try to find zircon in these rocks, and the oldest zircon that they can find are zircon dated at 3.8 or slightly less than 3.8 million years. So what most of the geologists believe now is that the Hadean age is some kind of artifact, and that the true age of emplacement of these rocks is 3.8 billion years. So these rocks are not Hadean rocks. They have some, in the memory of samarium-neodymium systems, they have recorded an older event in the Earth's history, but the age of the rock is 3.8 billion years. So they are not Hadean rocks. In other words, Akastagnices remain until today the oldest known rocks at the surface of the Earth. Okay, what is the problem with the Hadean Earth? During a long period of time, people, and still today, people think that the surface of the Earth was molten. There were meteorites falling each 10 minutes and so on. So that was a real hell, and this is the reason why this period is called Hadean, from Hades, god of hell. But since 15 years, people think that, in fact, maybe there is another alternative. That is what they call the cool early Earth, with continents, water, and we'll see other particularity of this. So there are two different views about the Hadean Earth. Was it a cool early Earth, or was it the hell? So we'll try to see some argument in favor of or against these propositions. First, you know that the Earth is made up of several shells. The inner one is a metallic solid core surrounded by metallic liquid core, a solid mantle, and of course a crust. So you know that there are continental and oceanic crusts, but there is a very thin crust at the surface of the Earth. And of course, outside we have ocean and atmosphere. But if we are speaking about rock, we have this composition. So one of the questions is, when does the separation between metal and silicate took place? So the dating is based on extant radioactivity, and there is a system that is very interesting. Is the decay of 182 hafnium into 182 tungsten. The half-life is 9 million years. And of course, all the 182 hafnium disappear in less than 60 million years. So this means that this system is very appropriate for dating events that took place very early in the Earth's history, before 60 million years after nucleosynthesis of hafnium-182. In addition, the behavior of these two elements, of the parent and the daughter, or son, as you want, is not the same. Hafnium is what we call lithophile element. So that means that he has affinity for silicates. So he will move in silicates. While tungsten, as Francis explained for platinum group elements, is siderophile. That means that it has a strong affinity for metal. So in addition to be appropriate for dating early event, they are also appropriated for dating the separation between silicate and metal, because parent and son or daughter element behaves in a completely different way. So let us imagine that the core mantle differentiation took place quite late, after 60 million years. So what does it mean? All hafnium would have decayed into tungsten. So they will not have any hafnium remaining. So the whole tungsten will be incorporated in the core. And there are no tungstens in the silicates. Now, if we imagine that the core mantle differentiation took place earlier, before 60 million years. So only one part of hafnium decay into tungsten. And this tungsten, of course, will move into the core. But some hafnium remained. And this hafnium will move into the silicate. And this is only when it will have been incorporated into the silicate that it will decay into tungsten. So that means that if we find, if we find some tungsten, 182 tungsten in the silicate, this would mean that the core mantle differentiation took place before 60 million years. So we can have an idea. Of course, if I explain this, this means that we have found some excess of 182 tungsten in the mantle. So mantle silicates contain this kind of excess, which means that the differentiation between core and mantle took place less than 60 million years after the beginning of formation of the solar system. So this is an important point. That means that certainly the differentiation between core and silicate took place extremely early. That was a very rapid event that took place very early in the history of our planet. Nothing? Okay. We can have more information. If we look here, this is tungsten isotopes. Here is time with a break here somewhere. So if we look at the evolution of chondrite in this system, we have this evolution as shown with a red line here. And in fact, if we look at the composition of the mantle today, the composition is here. So that means that this composition is not chondritic. There was a fractionation somewhere. If the composition would have remained chondritic, we should have this point here. So we have this point. And if we make some assumption on the, have you noticed a nice event? I play it again. I like it. So if we assume this ratio here, we can draw this line of differentiation. And the cross-section, the crossing between these two lines, the red and green, will give the age of the core differentiation. And we obtain a very young age, which is 30 million years after the beginning of solar system formation. So that means that this took place very early in the history of our planet. And some people consider that at that time, maybe the planet was not already formed as the planet we know today, and that maybe this kind of differentiation would have taken place in platesimal and not really in the planet. These are some consequences, because if differentiation took place in platesimal, that means that the accretion of platesimal to give the Earth implies that there was a second episode of differentiation into the Earth itself. But very probably this could take place into the Earth or into platesimal, so very early. Okay, there are some limitations to the method. What I presented to you is the ideal case where all hafnium decays into tungsten. In fact, some people realize that on the moon, some one isotope of tantalum that react or that is impact with a neutron can give also 182 tungsten. That means that we can have cosmogenic 182 tungsten. So this is not what is in this assumption. The excess, or one part of the excess on 182 tungsten is not due only to decay of hafnium, but can be also of cosmogenic origin. So this is a limitation for this dating. And another limitation is that we consider for this model that the 82 hafnium, the isotopic ratio of hafnium here, is the same in the whole solar system. And Francis discussed quite a lot the heterogeneity of the initial solar system. And so, okay, this is the assumption, but we do not know, we have no idea if in each part of the solar system this ratio was everywhere the same. So, okay, certainly the core and silicate differentiation took place very early, but the value of 30 million years is, of course, seems to be very easy to remember, but there is a lot of limitation for this value due to these problems. And maybe this is 60, maybe this is 100, but this is very early, but probably not exactly 30 million years. Okay, you know the structure of the Earth, and you also know that convection of movement into the liquid core, metallic core, induce the magnetic field. So this point is very important because when you know the effect of the magnetic field that protects the Earth from the solar wind here. So this is a protection that allows the atmosphere to remain and so on. So we have seen that the core was differentiated very early. So the condition for the apparition of the magnetic field were realized very early. But this doesn't mean that the magnetic field appeared immediately. We do not know if the convection is a outer core appeared immediately. So some people look at the magnetism in rocks or in minerals, and this is a diagram that I could have shown last year. And last year, I could say that the oldest record for the magnetic field was 3.6 million years, with a strong variation in the strength of the magnetic field. And recently, that was, I don't remember, I think last October, some people worked on oldest rock and they found some remnants of magnetic field in very old material, very old zircons, and it seems that at least at 4.2 there was a magnetic field on the Earth. So this means that the magnetic field appears maybe contemporaneously, but not very late after the differentiation of the core. And okay. And of course, if we look, for instance, here, this is not the Earth, but this is Mars. And you know that there are old terrains here, younger terrains here. And if we look at the magnetic field, the map of the magnetic field on Mars, there are, of course, we see that it exists only in the very old rocks and older than 4 million years and very probably older than 4.3 billion years. So that means that in planets just like Mars or the Earth, the magnetic field appeared very early. And this is something very important for the development of life and even for the prebiotic chemistry. Okay. Now, another part of the Earth history, I stop with the differentiation of core and silicate. One part is coming from the moon. So the moon, if you look at the moon, there are white and black parts. And something very interesting on the moon is that some person, this is not me, were able to take samples on the moon. But you see that even on the moon, geologists use hammer, exactly like on Earth. And okay, if you look at the moon, there are white parts that covers a very big surface on the moon. And of course, no surprise, the samples are white. And they consist in mainly or exclusively in plagioclase crystals. So here there is a lot of broken crystal due to meteoritic impact, but most of the minerals are plagioclase. And if we look at the rare earth composition of these rocks, we can see that the content in rare earth is very low, with a positive anomaly in europium. Now, if we look at the black rocks here, they are basalts, as you can see here, with plagioclase and pyroxene crystals, and they have a almost symmetric composition, very high content in rare earth with a negative anomaly here. And of course, what the first geologists who work on this sample concluded is that it's possible to differentiate both rocks from a chondritic value with a flat pattern that should be somewhere here. So there is some complementarity between the basalts and the anorthosites here. So probably these two kinds of rock were derived or generated or differentiated from a single rock. And in fact, what they imagined that this was not really a rock, but a molten rock, so that means a liquid, and that the moon was molten, they call this a magma ocean, so one part at depth was not remained unmelted, that means solid, and the external part was molten. So the energy for melting the moon is due to the transformation of the kinetic energy of planetesimal into thermal energy, due to the release of iron silicate by gravitational separation, of course the decay of radioactive source, and so on, and maybe tidal heating. So there is a lot of sources able to melt the outer part of the planet. Something interesting is now if we look at the crystallization of this. And if we look at the crystallization, here is the density of a basalt and the density of most minerals. And what we can see is that all the minerals that can crystallize in a basalt have a density greater than the basalt. So that means that when they will crystallize, they will sink. All the minerals but one, that is a plagioclase, that is a feldspar, that is a density lower than the density of the magma. So this one will not sink at the bottom of the magma ocean, but it will float at the surface. So that means that what we imagine for the moon is the crystallization with, of course, a cumulate made of, I will call this heavy minerals, just like olivine and pyroxene, so they will sink at the bottom of the magma ocean, and a plagioclase cumulate that will float and make an anorthositic crust at the surface of the magma ocean. So the behavior of some minerals will be different, some sink and others float. And of course this is something very important because they will form some kind of lid that will prevent a rapid cooling of the magma ocean. So what we can see is that anorthosite cover a very big surface of the moon. That means that the event of genesis of this anorthosite was a planetary-sized event. So that means that if we believe that these anorthosites are coming from crystallization of a magma ocean, that means that the magma ocean covered the whole moon. Another point is that the age of the anorthosite is 4.456 million. So it is a very old age, and the definition of this age is very good. There is a very good isochrone here. So that means that the magma ocean not only affected the whole of the planet, but was a very early event in the history of the planet. This was an event that took place before 4.45 million years. So very early in the history of the planet. Okay. So, okay, I was speaking about the moon. What about the Earth? Okay, if we, well, this calculation is very, is not detailed, but if we consider the energy released by accretion, by the impact, and if we consider that it was released instantaneously, we can see that on the moon the temperature would have increased up to 1,500, and of course on Earth, due to the bigger size of the planet, the energy release would have been higher. Another point interesting is that the gravitational acceleration is not the same on the moon and on the Earth. And this has consequences because plagioclase is a mineral that can crystallize only at low pressure. And of course, if now we transform pressure in depth in the planet, we can see that plagioclase is stable on Earth only from 0 to 30 or 27 kilometers, while on the moon, this is 165 kilometers. This is due to the fact that the pressure increases less with the depth if we compare with the Earth. So that means that if there is an anorthositic crust and a thick anorthositic crust on the moon, very probably this kind of crust is unlikely on the Earth because the thickness of the magma ocean able to produce anorthosite is small compared with the moon. So very probably we do not expect that the Earth had an anorthositic crust. However, if we look at rocks, you have seen this sample yesterday. If we look at komatiite, we can see that komatiite, if we look at old komatiite, older than 3.4 billion years, their composition, here is a chondritic composition. If we look at some rare earths or some major element, they have a very wide range in composition. This corresponds to, for instance, here, this group corresponds to this kind of pattern depleted in heavy rare earths, and this group here corresponds to pattern enriched in heavy rare earths. And we have everything from depleted, flat pattern, or enriched patterns. If now we look at komatiite at 3.4, there is a very big difference because all the komatiite after 3.4 have some kind of chondritic composition with flat patterns here. So what does this mean? This means that before 3.4, the mantle from which komatiite are generated was heterogeneous, strongly heterogeneous, and after 3.4 it became homogeneous here. So that means that the composition or the structure of the mantle changed in course of time. And in the early life of the mantle, there was some kind of internal differentiation into the mantle, and this differentiation disappeared after 3.4. So, okay, this is one argument that says something happened early in the history of the Earth with the mantle. But one of the problems with the Earth is that Earth is a very active planet. There is plate tectonics, there is erosion, alteration, and most of the old rocks disappeared due to these processes. But if now we look at the geochemistry of the old rocks on Earth, and if we use again this extant radioactivity, 142 neodymium, that marks a differentiation between some kind of silicate and other kind of silicates, for instance, between olivine and the pyroxene and so on, silicate-silicate fractionation. We can see here we have komatiite, mantle nodules, carbonatite, kimberlite, basalt from hotspot, basalt from oceanic ridge. And all these rocks fall in what we call the Earth standard. So for epsilon neodymium, this is between -8 to +8. So all the rocks coming from the mantle fall exactly in the same range. But there are, until now, we know 3 exceptions. And these exceptions are Isua gneiss, Nuvagittu gneiss, and Akastra gneiss. So that means that the oldest rocks that we know at the surface of the Earth today have slightly different composition. They differ from the Earth standard here. Some are enriched, others are impoverished. So there is some complementary behavior between the enriched and depleted rocks. So that they say that the oldest rock on Earth's surface recorded some kind of mantle differentiation in the early mantle. We can find this kind of structures. So this, together with the, for instance, chondritic or not chondritic composition of the early mantle, are arguments in favor of magma ocean on Earth. But there is a problem. And the problem is that we do not have anorthositic crust. It's unlikely to have crystallization of huge amounts of plagioclase. And in fact, the mineral that will crystallize instead of plagioclase is garnet. And garnet is a very heavy mineral. So the garnet will sink into a basalt. So that means that on the Earth, what we expect is to have crystallization of the magma ocean with olivine, pyroxene, and garnet that will sink and form a cumulate at the base of the mantle. So there is no crust, there is no mineral floating at the surface of the magma ocean. And this is some kind of problem, because if we have not a stable crust, the magma ocean will cool extremely rapidly, too rapidly to allow the fractionation and the sinking of the minerals at the bottom of the magma ocean. So this means that certainly there was a crust. And one researcher that you know, that was Francis Albarrad, proposed that this crust could have been serpentinite. Serpentinite is due to the action of water on basalt, for instance. And water can be liquid water, but can be water as gas in the atmosphere. But if there is a reaction between the olivine and pyroxene minerals in the basalt with water, they will be transformed in serpentine, and serpentine has a very low density and will float and form a crust that will prevent for a rapid cooling of the magma ocean. Something also interesting, as shown by Francis 1 hour ago, is that this kind of reaction will release some gases in the atmosphere, and these gases will favor reduced atmosphere that will be favorable for some kind of, let us, Miller reaction for the genesis of some evolve and molecule, just like amino acids and so on. Okay, so this is what we think about the magma ocean. What else? Okay, so I will try to summarize. So the idea is that there was a core here in one part of the mantle that was molten, a magma ocean, and maybe a serpentinite crust. Very early, before 4.4 billion years, there was crystallization of the magma ocean with sedimentation of pyroxene, olivine, and garnet. So there was a part enriched in garnet here, depleted in garnet here, for instance. So there were at least 3 parts in the mantle. Chondritic part, garnet enriched, and garnet impoverished here. So this crystallization in the magma ocean generates some heterogeneity in the mantle. So after 4.4, everything was crystallized, and of course convection began to play and to mix these different parts. And depending on the parts that will melt, garnet enriched, not affected by melting, garnet impoverished, we will obtain all the kinds of komatiite we found here. Some parts here are garnet enriched, garnet impoverished, not affected, and so on. So we can explain like this the genesis of all this kind of komatiite. The mixing, I don't know if the mixing will be complete or not, but people consider that mixing will result in rehomogenization or some kind of rehomogenization of the mantle. And of course, as the garnet enriched and garnet impoverished part are complementary, they will result in a chondritic mantle. And of course, this accounts for the composition here of the chondritic komatiite after 3.4 billion years. One point that is interesting is that this magma ocean started very early. So if we consider that the magma ocean appeared very early at the very beginning, this would also create favorable conditions for silicate iron separation, of course. It will be more easy to have drops of metal sinking in liquid than in a solid. So this is one of the way by which people consider the possible separation of metal for in the Earth. So the metal drops appear here in the magma ocean and move towards the core itself. Okay, this is not a magma ocean, but this is a picture of a lava lake in Ethiopia. Okay. Now, I would like to say a few words about continental crust. During a long period of time, we had no evidence of the presence of continental crust in Hadean times. We have indirect evidences. For instance, here, if we consider the mantle, if now we consider the composition here of the continental crust, of course, if you extract this continental crust from the mantle, you will impoverish the mantle. So the mantle resulting from the extraction of this continental crust will be impoverished in some elements. So even if we don't know all the continental crust, if we look at the composition of the mantle, maybe we can have an idea of when the continental crust began to be extracted from the mantle. And if we look, for instance, at here, neodymium isotopes, here is time. And what we can see is that in the oldest rock, at 4 billion years, here, as early as 4 billion years old, we have rocks that are depleted. The chondritic value is somewhere here, and depleted rocks are above this line. So that means that very early, the oldest rocks that we know are already depleted. That means that they are coming from a depleted mantle. So if the mantle was depleted at 4 billion years, that means that before 4 billion years, some continental crust has been extracted from this mantle. So that means that continental crust began to be extracted before 4 billion years. Even if we do not know this continental crust, we have indirect evidence of its extraction before. Some calculation indicates that probably between about 10% of the volume of the present-day continental crust has been extracted before 4 billion years. So this is true for neodymium, but if we look at strontium isotope or hafnium isotopes and every kind of isotopes, we can see that depleted mantle appeared very early in the Earth's history. So about Akasta, I spoke about zircon, and I would like to say a few words about zircon. Zircon is a silicate of zirconium, and this mineral is extremely resistant to weathering. Maybe you learn when you are in a small class that weathering of a granite, quartz is very resistant to the weathering of a granite. Zircon is more resistant than quartz to the weathering. Its melting temperature is very high, and something very interesting is that it contains uranium and thorium, and no lead. So this mineral is wonderful for dating, because the whole lead that you will find in zircon crystal will be lead made by disintegration, by decay of uranium and thorium. So this is ideal case for dating. And here, for instance, is a biotite crystal. And into the biotites there is a zircon crystal, and you can see a dark zone all around. And this is due to the radioactivity of the zircon, so the decay of uranium and thorium, that modify the lattice of biotite and give this color. So, okay, this mineral is very radioactive. And another picture, here is a zircon crystal, and you can see a lot of cracks all around. And of course, when you transform uranium and thorium into lead, the ionic radius of uranium is small compared to lead. So when uranium decays into lead, the size of the mineral will increase because you transform an element with a small ionic radius into an element with a big one. And as the mineral increase of size, it will break the minerals all around, and these cracks are due to the increase of size of the zircon. Okay, nothing to do with the following of the talk. Something also interesting is that technology has made a lot of advances, and you can see here, this is not a zircon, but these are other minerals, and each one of these are all made by laser, and this is a technique of laser ablation. So you can vaporize some part of the minerals and analyze this part, and obtain, if you analyze the isotopes, you will obtain age. So I present you one part of Australia. This is Jack Hills in a Pilbara area. And in this area, you can find rocks that are sediments. Here, these are sandstones, but in some places you can find conglomerate. And these rocks contain a lot of zircon crystals. So here are some of these zircon crystals. And these zircon crystals are very famous because they give old, very old ages. So for instance, this zircon crystal give ages of 4.35 million years. And even one part of this crystal here gave a very old age of 4.4. This age, some people discuss this age because, as you can see, this age is located, the analysis was made along a fracture zone here. So some people say, okay, maybe the age of 4.4 is due to the fracture and some modification of isotopes, but these ages are absolutely certain. So these are very old material. So, okay, Akasta are the oldest known rocks. Here, this is not a rock, this is only a mineral. This mineral is in sediment. So the rock in which the sediments are contained is only 3.7 or 3.8 billion years old. So we do not know in what kind of rock these minerals crystallize, but these are the oldest material known on Earth. And you can see that this age, if it is true, is more or less the age of the end of crystallization of the magma ocean. Okay, here is a frequency. This is an old diagram. It is from 2004. Here are the ages measured on different zircon in Jack Hills, and here's the amount of zircon analyzed with this age. And what we can see, even if the data are old, is that the ages at 4.35, or the ADN ages, are not an accident. This is not due to melting, due to meteoritic impact or something like that. Zircons were generated all along the ADN times, with a maximum between 4 and 4.2. But this is a permanent thing. So this is not an accident. This is something that was very common during the ADN times. So these zircons were studied, of course, a lot of study about these zircons. And generally, people say, okay, zircon can crystallize in granite. But we know in some places, even in France, near Le Puy-en-Velay, we have some zircon in basalt. So, okay, one of the first questions is, this zircon, what crystallized in what kind of magma? What was the magma host for these zircon crystals? So the zircons, when they crystallize in a magma, can catch or incorporate into their structure some minerals that are crystallizing together with them. So some small part of the minerals that are crystallizing together with them in the magma can be incorporated in the zircon. So there are no as inclusion in zircon crystal. And here are some of this inclusion. So in red there is quartz, green plagioclase, rutile, muscovite, biotite that are mica. And if you look rapidly, there is a lot of quartz everywhere. You know that quartz is very common in granite, and there is no quartz in basalt. In basalt, you would have olivine, pyroxene. There is no one here. So obviously, this rock crystallized in a granite. So if we consider that there is quartz feldspar, mica, that means that the host magma was granitic in composition. And of course, granite means continental crust. So that means that as early as 4.4 or 4.35 million years, continental crust existed on Earth. So the first continental crust appeared very early at the surface of our planet. Okay, the same in yellow. But, so that was something very interesting when the zircon were discovered 15 years ago. But the lattice of zircon can include some elements, just like titanium here. And of course, the lattice is more tolerant when the temperature is high, and less tolerant when the temperature is low. And there is a correlation between the amount of titanium in a zircon crystal and the temperature. And here you have this law, this is a log of titanium. Here is the temperature. So if you take a zircon crystal, you measure the titanium content, you can have an idea of the temperature of crystallization of the crystal zircon. And so this is what appeared here on the Jekyll's crystals. And we obtained a very surprising result, because everybody imagines that the early Earth was very hot, very warm. And what we obtained are, I would not say very low temperature, because 600 or 700 degrees is not low, but low compared to what we could expect. The crystallization temperature was very low, and the maximum is about 700 degrees. So everybody expected very high temperature, and in fact, this temperature were low. This has some consequences. If we look at the granitic system, we have here temperature, pressure or depth, and here is a dry solidus for a granite, and here is a hydrous solidus for granite. And so this is something you learn when you are very small, that water decreases the temperature of a solidus, and it's easier to melt a rock if you have water available. Now, if we look at the crystallization temperature obtained from titanium isotope, we can see that there is no way to have crystallization at that temperature if we have a dry system. That means that we needed to have water available in the system. So this is something very important. So you will say, okay, it's not necessary to look at titanium. We have seen that there was biotite and muscovite that are water-bearing minerals. But, okay, this is another argument in favor of hydrous melting and availability of water in the system. I will continue with these zircon crystals, and some people look at the oxygen isotopes. If you look at the oxygen isotope, Francis told you about this system. Here is the age of the rock, and here is a composition of zircon composition in mantle conditions. All the data, or almost all the data, from the Jekyll zircon give delta 18 oxygen greater than the mantle value. And there is only one way to obtain this, is low temperature hydrothermal alteration. So once again, we return to the fact that there was water available in the system. There was water. And people say, as this is low temperature, as we know to have some weathering of the parent rock before melting, to give the magma in which zircon crystallized, this means that there was water, lakes or ocean at the surface of the planet at that time. So one of the conclusions of a paper published 10 years ago was that this isotope proved that there were ocean at the surface of the Earth at 4.4 or 4.35 million years. So very early in the planet history. Okay, you do not believe in oxygen isotopes, so we'll look at lithium isotopes. So if we look at lithium isotopes, here are the mantle values, and here are the values measured in Jekyll zircon. And what you can see is that some of this value plot in the mantle array here, but we have very low value up to minus 20 here. So very low 7 lithium isotope value, delta 7 lithium. Now, if we look at other Archean rocks, just like growing gneisses, the TTG, or sanukitoids that we have seen, this value plot more or less on the mantle field and do not show these strongly depleted values that we can see in Jekyll's rocks. So now look. Wow. Wonderful, isn't it? If we look now at modern continental crust, we have more or less the same as in Archean rocks. So the modern continental crust, the lithium isotopes, are in agreement with mantle value, and we have no depleted value. The last one, well again, are weathered continental crust. So this modern continental crust, but altered by the rain, by fluids, and so on. And if the modern continental crust is weathered, the delta 7 lithium will decrease down to minus 20. So that means if we compare these diagrams, that means that the Jekyll zircons have a composition identical to the composition of altered continental crust. And alteration of the continental crust is due to the effect of water on this continental crust. So obviously there was water at the surface of the Earth at that time, at 4.4 or 4.35 million years. So very early, just after the accretion, or more exactly, just after the crystallization of magma ocean, there were continents and water. And Francis told you in the introduction of his talk that water and continents are something important for the apparition of life. Just something for fun. Some people discover in these zircons graphite. So there are some pieces of graphite here into the zircon crystals. Or graphite, you know, is carbon. And the people who work on this is a paper that was published, I don't remember when, but September or October 2015, so a few months ago. So this person compared composition of graphite from Greenland here and from graphite here from Jekyll's zircons. And one of the arguments of the paper is that if we look at here the isotopic composition of carbon, we have here the range of composition of carbon isotopes in rocks, ocean, atmosphere, and so on, so inorganic matter. And here we have the range of composition of organic carbon. So of course this value overlap here, but there is a place here which is only occupied by organic carbon. So one of the conclusion, or possible conclusion, as said the author of this paper, is that Jekyll's graphite, as well as the graphite in Greenland, could be due to, could be considered as geochemical traces for life in this early Earth, because the isotopic ratio here is very low. This is okay, but they forget something important, is that if this rock underwent some metamorphism, so if they are heated and submitted to high pressure, the isotopic ratio will change. And here is the composition for metamorphic rocks. So metamorphism can change this isotopic ratio into this kind of isotopic ratio. So we know, because we have the rocks in Itsua and Aquilia in Greenland, we know that these rocks are strongly metamorphosed. So probably the isotopic ratio, the low value of delta 13 carbon are due to this metamorphism. Of course, here we have only zircon crystal, but one of the problems is that you do not know the history, of course, of this graphite, but probably this rock also underwent very high temperature. And one other part of the problem is that in Itsua and Aquilia, graphite is found in rocks that form at the surface of the Earth. Here, in Jekyll's, graphite is found in zircon crystals that form into a magma at depth. So it's difficult for me, at least, to imagine that life could have developed at depth in a magma or something like that. So, okay, this is a very recent result, but we must take it with some kind of precaution and some care. Well, maybe the Hadean Earth was something like that, with continent and water. The origin of water, you know, you are the specialist for that. And so you know everything about. Now, if we look at the moon, if we look at Mercury, even other planets, there are, I would say, planets without plate tectonics or without erosion, alteration. These planets are full of meteoritic impact. Okay, I like this meteorite for its name, Eros. And even the small bodies are full of impacts. So if we look here at the number of impact craters on the moon, and here is the time, of course, we have this in different places. We have these points. And from this point, it's possible to draw a line like this. You must notice first that we do not have on the moon craters older than 4 billion years. We have no craters here. So the older one is this. And of course, one of the ideas, the first idea, was to say, okay, what we see here is the end of the accretion. And it's possible to extrapolate the curve like this, just until this point where accretion took place. So this is the end of accretion. So we can have something like that. And in fact, if this is true, that means that if we go back in time, the amount of meteoritic fall on the Earth's surface increases. And probably the surface was something like that. With each 10 minutes, you have a meteorite falling down on the Earth's surface. There is a lot of problem with that. And one of the problems is that if we go back here, and as it's possible, if you know the size of the crater, impact crater, you can know the size of the impactor, the size of the meteorite, and the mass of the meteorite. And in this condition, it's possible to calculate the mass that was coming at the moon surface at each period of time. So if we go back like this, we can find that the moon was totally formed at 4.1 billion years, which is absolutely false. It's not the reality. We know that the moon formed much earlier in the solar system history. So this means that we are not allowed to extrapolate this curve like this. So today the more common proposition is something like that. We have accretion of the planet with an intensity of impact that is very strong. The intensity of impact decreases until a level which is more or less slightly higher than today, but not very much. And there is an accident somewhere here, which is called the late heavy bombardment, that took place more or less at 4 billion years or 3.9 million years. So this is a punctual event, but that means that before this event, the Earth was what is called the cool early Earth, and we know that there were water, magnetic field, and there was also continents on the Earth at this period. So maybe the Earth could have been something like that in this model. So there is a strong difference between between this model and this one. So one of the questions is, what is the origin of the late heavy bombardment? So probably you know as much as me about this. So what's the model proposed 10 years ago in order to explain this? And the idea is that there was a migration of the planet due to Jupiter migrating slowly towards the Sun and Saturn away from the Sun. And when they enter in resonance, everything was disturbed. And probably, so here is an idea of what was the solar system before the bombardment. So here are the main giant planets with a disk of platesimal. And the result is something like that, is a present-day solar system. So the orbits are less concentrated towards the sun, and of course the Kuiper belt is by far smaller than the platesimal disk. And certainly, you know, this that is presented by Morbidity and NIS. This is a NIS model. So you have time for drinking something. So because the event took place at 800, and you see here is Jupiter, Saturn, Uranus, and Neptune here, and the disk of platesimal. And at 800, you will see that here you cannot see that Jupiter is slightly migrating towards the sun. That means it's perfect for drinking something. You have seen nothing, I suppose. So I will proceed slowly. So this is a situation at the beginning of a Earth, of a solar system formation. So progressively, Jupiter migrates slowly towards the center of towards the sun, and just before the late heavy bombardment, situation was something like that. So you can see that the orbit were greater than at the beginning, and at the moment of bombardment, of course, you see that Neptune and Uranus mainly enter into the platesimal disk, and of course disturb totally the system, and the object in the disk move, of course, outwards, but also inward towards the sun, and they create the bombardment. So this is the final position in the model. And maybe we can imagine the situation that is something like that. So probably I was not there the first day, but you heard about the migration of Jupiter and Saturn in the very early solar system here. And after, the situation was relatively stable, and something happened, that is a late heavy bombardment. And when this took place, when Jupiter and Saturn enter in a 2-1 resonance, and the external planet took their present-day position in the solar system. You would say that, okay, this is a model, and this model is perfect because it can explain the late heavy bombardment. In fact, this model doesn't explain only the late heavy bombardment. It also can account for Uranus, the axis of Uranus that is perpendicular, more or less perpendicular to the axis of rotation of other planets. It can account for the presence of Trojan, so the meteorite in the Jupiter orbit, and so on. So this model doesn't explain only the late heavy bombardment, but also other characteristics of the solar system. So which is not a strong point in favor of this kind of model. On the moon, we have seen that the oldest impact, and here this is the oldest melted rocks, are 3.94 billion years. We do not know impact or significant impact before. On the moon, the crust is preserved. That means we have an orthosite. If we should have had a very strong bombardment of meteorite during 500 million years, this crust would have totally disappeared, and the crust is well preserved. So this is something in favor of just a short meteoritic bombardment. Short is 100 million years. So, okay, Francis talked about this. We do not know impact crater older than 4 billion years. And, okay, this is what I said, that continuous bombardment during the whole ADN would have totally rebuilt a moon in very short time. What about the Earth? About the Earth, okay, we know that some crust has been preserved. We see that we have old zircon at Jack Hills. We have old zircon in Acasta, the core of the zircon. And last year someone were discovered in Brazil also. So in some places this crust was preserved, even if after it has been eroded, but we have remnants of old crust. So the argument is more or less the same as for the moon. If some old crust has been preserved, that means that the bombardment was not so strong. We have also evidence that water was available on Earth's surface. There was liquid water. And of course, in case of heavy bombardment, it's difficult to imagine that this water remain on the surface of the Earth. This water would have been vaporized by the energy of the impacts. And also in Isua rocks, so that are supracrustal rocks deposited at the surface of the Earth, people found some anomaly in tungsten isotope that are consistent with the meteoritic contamination. So maybe they could reflect the heavy bombardment. There are two arguments that are not in favor of this. Nobody discovered what we call shock quartz crystals. So that means that under the place in a meteoritic crater, the crystal of quartz are shocked. They acquire special textures that is characteristic of this impact. We do not know this in all very old rocks. And in Isua, again, we should expect a chromium isotopic anomaly in case of meteoritic bombardment, and we do not see this anomaly in Isua. But Isua deposited at that time 3.865, and maybe that was the end of the meteoritic bombardment was finished at that time. We don't know. So, okay. Nice picture of a meteoritic bombardment. So I will finish with that and just saying a few words about life and the compatibility of life with what I have said. Of course, if we consider the very early ADN time here, so between the beginning of accretion and 4.4, the end of crystallization of the magma ocean, for me, it's very difficult to imagine that we could have life or even prebiotic chemistry because we had a magma ocean. That was the end of the accretion. So for me, it's very difficult to imagine even prebiotic chemistry in a magma ocean. So for me, I consider that life was more or less impossible at that time. In the late ADN, after 4.4, we know that we had continental crust, ocean. We know that the magnetic field was active at that moment, so the Earth was more or less preserved from the solar wind. So the conditions were favorable for life. I do not say that life existed at that time. We have no evidence for that. But the conditions were favorable for prebiotic chemistry and emergence of life. And of course, during the Archean, after 4 million years, we have evidence that life existed and that life evolved during this period. So in this history, there is only one important unknown, is the role played by the late heavy bombardment. What was the role played by this bombardment? And was it strong enough for sterilizing the Earth, if life existed before, or not? So this is a very important point. And this has some philosophical consequences, of course, because if life appeared here, let us imagine that life appeared here, disappeared due to the late heavy bombardment, and of course appeared after. That means that life is something very common. This is not something exceptional, but we need to have some condition, and if we have this condition, life will appear. This would mean that life appeared twice on Earth. So some people consider that the heavy bombardment was strong enough to vaporize the ocean and so on. But recently there was a lot of paper indicating that probably this was not strong enough for vaporizing the whole ocean. So if one part of the ocean were vaporized, other parts remain liquid. So probably, it seems that most people think that the late bombardment was not necessarily a sterilizing event in the history. So I think that these things are reasonably established, and the great unknown is the role played by the bombardment.